Recording in progress.
Okay, guys, quiet. Thank you. So, just to, because now everyone's will have taken this because they have 4 people taking it right now. So, anyway, for number 1, I think that was pretty. I haven't graded them yet, so I'll grade them hopefully tomorrow and get back to you guys Friday. So for number 1, you should get B hopefully. That was pretty straightforward. 1 point. So, because the ratio is going to be √3. Because r squared is 3, so r is √3. You go backwards. But it could be negative √3 as well. So ratio, so that's a possibility. Yeah, or it could be negative √3. For number 2, the answer is E. And that one, if you just kind of do a pattern, you start noticing 1, 3, 4. So it's actually called something like a Fibonacci sequence. Like you kind of just do that over and over again. And you start noticing that the first 2 are odd and third one's even. First 2 are odd, last one's even, and so forth. So that's what's happening there. So when you go from L1, L2, L3, all the way to L2023, how many terms are even? So you'll see that if you do 2023 divided by 3, that's 674, the remainder of 1, right? And so 674 means you have 674 groups. So 674 even numbers. And then the remainder of 1 is just an odd number, so don't worry about it. So that's the thinking there. Now, by the way, all these problems, I'm not sure if you guys recognize this. These actually all came from the AMC exam. I'm not sure if you guys, they all came from the AMC exam. So I went to the AMC. Actually, I went to a website called The Art of Problem Solving. And so the point I'm trying to make is that when you guys prepare for tests, sometimes we teachers, sometimes we do use online resources. So do you consider, I mean, I'm not going to do that again because I already told you now. Plus, we're doing calculus today, so I'm not going to be doing that again. But sometimes we do that. We do look at online resources. You know. So it was kind of nice because these were all AMC 10 exams. And they just do the series. Now, for number 3, guys, quiet, please. Thank you. The answer is B. And again, I'm hoping these instructions are clear, but I know a lot of graphs. Well, what's the area? So this right here is area 1 for one area. That's another area. And so if you set up as a arithmetic progression, right? So that's x and 1. So the first area is x. The next one is going to be all this minus the inside. So you're going to do x plus 2 as the width. The height, of course, is 3 because subtract by the inside, which is x. And the third term is going to be this. X plus 4 on the outside times 5, that height, but then minus the inside, which is x plus 2 times 3. Clean it up, you get x, 2x plus 6, and 2x plus 14. It's pretty clear the common difference between the first 2 is x plus 6. The common difference between the other 2 is going to be 8. Solve for x, you get 2. Pretty easy after that. So it wasn't too bad. For number 4, the answer was D as in dog. You have 8 terms, looks like, you're adding up. And actually it goes in a group of 8, I believe, if I'm not mistaken. Because, guys, quiet. So if you add up all the numbers first, again, it's like it's a remainder when you divide, we add the 2 and divide by 3. So right now the remainder is hold on. If you add, if you plug in 2 for n, sorry, 2 for n, you get 1. 1 divided by 3. Yeah, it starts at a 0. Wait, what? Does that make sense? It repeats. Yeah, no, I know. The pattern goes like this, basically. 0, 0, 2, 2, 1, and then repeats after that. Exactly right. Well, let's try to make sense of this here. Those added up. Yeah, the remainder. Yeah, okay. So anyway, yeah, adds up to 9. There you go. So that's why it's 9. Oh, thanks. Appreciate it. Thank you. All right. Okay, let's keep moving. Number 5. That one I thought was I actually kind of messed up initially because I made a little careless there, but the answer is E for that one. Yeah, it was kind of tricky. What I did was this. Guys, quiet, please. So if I subtract the first two terms, right? Second minus first, you should get negative 2y. So I'm calling that D, the common difference. And if I subtract the third and second, I get this. And that should be xy minus x plus y, right? And that will also equal D, or negative 2y. So then you should have xy minus x equals negative 3y. And then also, if you do the fourth and third terms, you have x over y minus xy equals negative 2y. But you can multiply both sides by y, of course, right? And so that's x minus xy squared equals negative 2y squared. Then what I did was I took this right here. I isolated x. So that's, yes, Brooke? Not right now. I have to take care of this. Sorry. Just move on to another problem. Oh, right. Yeah, exactly. Well, I didn't notice that. It's okay. She didn't mean to. All right, okay. Thanks, Carl.
Anyway, you have this. So you replace y with that. Well, first of all, y is canceled here. Replace y with that,
And then keep working through the motions. You should be able to get y equals negative 3/5. From there, you should be able to get x, and you should get the rest of the answer after that. So that's just kind of give you a little bit of an idea of what happens. 6 was 80, 70, or E. And I'll try to do my best to be kind of a partial credit. But you just find a pattern. So A3 is 3/11. Then A5. I got 9/45 when I worked out, but it actually reduces to 3/15. If you reduce to 1/5, you may not see the pattern. That's a problem. So that's A4. That's A4. A5 is 3/19. A6 is 3/23, and so forth. So what happens, guys, quiet please. Thank you. So what happens is that you keep increasing the denominator by 4 while the numerator stays at 3. So then you treat it like an arithmetic progression, right? And since you want to get the 2019 term, the bottom would look like this. 3 up top, of course. 11's the first term, plus 2019. And because the third term was 11, I'm doing 2019 minus 3, or 2016 terms after that, I guess, to get that. And you get, and then we add up the two values, you get, yeah, I think you get 8075 for the bottom. Add the 3, get 878.
What was that relatively prime?
I don't know. That's weird. I don't get that.
I
I don't get that.
Oh, I don't know what that's about. It's because like, well, it wasn't an option in there, but if there was like a number that was like twice as big as E, it could have been like, instead of like 1/10, it could have been like 2/2. And they both.
Oh, got it. Okay.
Oh.
So they don't share any factors. Okay. All right, for 7, guys, quiet. The answer is D. That one's kind of tricky too. S20. If you calculate S20, guys, quiet. You'll get this. Remember, the 20th term is 38 more than the first term. Divide by 2 times n. If you clean it up, you should get A1 plus 19 times n. S60, if you clean that up as well, you get A1. So well, you got to figure out what A1 is. Well, hold on. No, that don't have to battle. So the ends cancel. The ends cancel when you divide those two, right?
Wait, Mr. Reed, if you get the right answer with no work, is that more?
No. Anyhow. The first term's A1. So are you asking how I got S20? Okay. Yeah, so it's A1 plus AN divided by 2 times n. And AN's A1 plus 38. Because A20, right? Because the 20th term, because the common difference is 2, right?
Oh,
you 19 times 2 plus the first term. Yeah. So when you divide these two, when you do S60 over S20, it just reduces to this, right? So the n's cancel. That's why n doesn't really matter. But then figure out what n is, sorry, what a1 is, that's the tricky part. So one way you could do is you figure, well, if it doesn't matter, right, then this would always, like something like this will always be true, right? We know this to be true. So that's 3a plus 6, by the way. That's just a. That's 6a plus 30. And that's 2a plus 2. Solve for a, you should get 1. So now a is 1. You have the ratio. So we have, so you want to get S20. S20 is going to be A1 plus 19 times N. Well, N is 20. A1's 1. And that's how you get 400. So that's how it works. And lastly, the extra credit. I didn't work it out, but the extra credit is E, 206. I think so. So, all right. I'll grade this by tomorrow, hopefully. Okay.
Works on another day.
Okay. So guys, here's the plan. Guys, quiet, please. Guys, quiet. Thank you.
So we're now moving on to calculus. Okay, so guys, quiet. So a lot of stuff we're going to do is similar to the first probably 2 or 3 months maybe calculus ED. So you guys might want to opt in to do that. Like maybe you have a busy schedule, maybe that makes sense to you. I think everyone in this class should be BC, by the way. I will recommend BC for everybody. So you guys do, you guys are great students. But you know, if you do want to do AB for some reason in the fall, a lot will be a repeat. And I'm going with different notes than AB. So that's not AB. So I actually have my own notes, but I decided to do the notes that the previous pre-calc BC teacher had done, just so there's not a repeat. You couldn't do AB the ball. But we are going to cover limits. That's kind of the first thing we did that helps us out in calculus. Then we do derivatives. It's going to stop at the technique and application. The goal is to try to get the first calculus equals by April 12th. And so let me look at the calendar to see. I think you can be able to get there. If I have to push it out another day or two, I might do that. And then we're going to do between 2 parts, 2 tests. So we're going to try to adhere to those test dates.
I'll look at the calendar just to see that makes sense.
Right.
It's pretty close, yeah. But we do have 4 meetings. We have a meeting today, meeting on Friday, then 2 meetings. Now, I understand that the sophomores are gone. So I may have to move that date. Yeah. The more I think about it, I may have to move that date. Yeah, so because sophomores are gone for a retreat. Yeah, so I might have to make this.
So it may just do this all day, but
so what this means that I may have to move the test date because we have 4 sections for this chapter, and then they're pretty long. And I'm spending a lot of time kind of talking about this stuff. So I'm not sure how far we will even get with part 1 today of this chapter. So anyway, yeah, I may have to move that test date before I think about it now. Anyway, everyone has copies of the notes? Yes? Everyone's got copies of the notes? Great. So let's get to the notes right now. See how far we can get. And also hand out the homeworks too.
yeah, here are the homeworks. So the whole goal is to cover it. So, you know,
The lot of advantage students that takes things in right?
3 more tests.
I'll just like this.
Last year.
Anyone that's studying. I'm sure you could. Not everyone. Yeah. Yeah. He said you would not go to service. I would. $50. I would not. I would not.
All right, guys, we're getting started. Here we go. Okay. Guys, quiet. Thanks. All right. And looking at the time, just make sure I'm pace myself appropriately. We go till 1:30. So let's see how far we can get. If we can't finish, that'd be great. I don't know if we can. 7 pages a lot. So maybe we'll trim down the homework a little bit. So intuitive introduction to limits. So limits, guys, quiet, are the foundation of calculus. Might seem a little artificial at first, like let x approach a number, but you never really get there, right? So how can we learn to enjoy them or make sense of it? So what is a limit? So basically, it's basically a point, again, that you're approaching, but you don't observe, like something you get really, really close to. Give you a good example. You know, if I have like a little curve here, and say it's like a hole, and say the hole's at 1, and say it's at 2, you would write like this: the limit as x approaches 1 of f of x equals 2.
So if you think about what that means, I find the exact value of 1, no. Because there's no point, there's a hole there, right? You guys talk about holes, I think, in actually I probably with you guys or not. I did, yeah, I forgot. We did talk about it, doesn't fall. So as you get closer and closer, it's all about approach. Those are all about approach. So it may not get there exactly, sometimes it does. Like what if I actually have that filled in?
Great. Then just tell me what y equals at 2. Sorry, at 1. Tell me what y equals at x equals 1. But if it's not filled in, it's all about approach. So in layman's terms, a limit's really what y approaches as x approaches a certain value. That's what it means.
But we write as a symbol like this, symbolically, we're at LIM, which is short for limit. X arrow 1 means what x is approaching. Fx is a function you're working on. And then equals is whatever number y is approaching.
So it's just a concise way of expressing all those words, right? What y approaches x approaches a certain value. So how do we make a prediction? You know, you could obviously go to Desmos or TI-84 calculator and zoom in and get close. And sometimes you can see that. So there's a numerical way of approaching a limit. Just seeing like, hey, let me plug in 0.9 or 0.99 or 0.999 or to the right of 1, like 1.01, 1.001, and so forth. And why do we need it? Because there are a lot of, like, I guess, black hole scenarios and quotes, like divided by 0 or things going to infinity. There's just a lot of wackiness with expressions where we kind of don't know what is going on when x goes to a certain number. So that's why we have limits. But also, it's a foundation for derivatives. In order to understand what a derivative is, which is a rate of change, which is kind of the first big part of calculus. It's usually like the first semester. Like we took like a college level calculus class. Sometimes you do 1/4. It's just all differential calculus. It really sets the foundation for that. And it'll make more sense as we do derivatives later in spring. So let us ask what if we can directly observe a function of value like x equals 0, x growing infinitely. We don't need a prediction. So limit is kind of a wonder. If you can see everything except some value, what do you think is there? And when our prediction is consistent and improves, the closer we look, we feel confident in it. So just some sort of little blurb on limits that we see there. Now, geometric approach. Let's take a look at that on the bottom of the page. So what do you notice first? You see a polygon, right, inside of a circle. And what's happening with each polygon? With each subsequent polygon, we're adding a number of sides. Right? First, you got a triangle, then a quadrilateral, then a pentagon, then a hexagon, septagon, octagon, nonagon, decagon, and so forth, right? So what's happening is that as
the number of sides is very, and the number of sides. Isn't the polygon sort of close to like a circle? Isn't the area again pretty close to the area of the circle? I mean, will it be exact? No. But will it be awfully close? Yes. So that's the whole limit. It's about the approach, right? So P, actually in this case, I guess you use perimeter. I was saying area, which you can think of like that way too, I suppose. But let's actually back up a little bit. I guess it's not for perimeter, not for area. I thought it was for area initially. So the perimeter will be pretty close to perimeter circle. Perimeter circle we call what? Circumference, which is 2 pi r. But these are not truly circles, but they get pretty close. So yeah. So you can think of like that as well. So that helps.
That's kind of a nice visual. Okay, now we get to the more boring formal stuff. Limit definition. So again, the question is, what is a function doing as x gets closer and closer to c? That's in layman's terms, right?
So if you think about it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 words that are expressed more concisely like this. So in layman's terms, all that this like mumbo jumbo, this like letters and mathematical stuff is what you see up above the quotes. That's what we have. These symbolic things to express what we want in a more compact way, right? So the limit of f(x) is equal to c is L, if and only if f(x) becomes arbitrarily close to L. Right, so yeah, we see what's getting close to it as x is close to c from either side. That's actually key right here. That statement
From either side, that actually is incredibly important. I'll explain why in just a sec. From either side, because sometimes you can see stuff like this. Let's say I call this C here, right? And let's say I have this. So that's a piecewise function, and we're going to deal a lot with piecewise functions here. And let's say it's like 1, and say it's at 2. So would the limit exist here?
no. From the left side it's approaching 1, but it's approaching the right side. I think we're done, right? That leads to something called continuity, which we're not going to have that discussion yet. We will, I think,
In the second or third part of the notes, I have to look again. I think in the second part of the notes, we talk about continuity. In this case, the limit does not exist because it has to be approaching the same value from either side. So from the left side, it's going one way, right side is going another way. They don't meet up. What kind of functions do this again? Piecewise functions. And that's something we can just concoct on our own, right? So I could say, hey, one side's like y equals x minus 2 squared when x is less than 2 or something like that. The other one's like a linear function, like maybe, I don't know, x plus 2 or something like that when x is bigger than 2. So that's what's happening there. It says note the existence or non-existence of fx at x equals c has no bearing. So if I were to redraw this, now here the limit does exist, but whether there's a point at x equals c doesn't matter. We don't care. It's all about approach. Whether it's filled in or not filled in, it doesn't matter in the case of limits. Okay, so let's approach this numerically. That's a good thing. So we're trying to find the limit as x approaches 2. Now, I'm going to kind of give you the quick and easy way. The quick and easy way, honestly, is factor, simplify, and plug in. Algebraically is going to be the best approach. Because if you think about how's a top factor? What cancels? And what are you stuck with? Right. And if you plug 2 in, what do you get? You are correct. Thank you. It is x minus 1. My bad. You're 100% correct. So right. So if I plug 2 in, what do I get now? 1 exactly. So I know that's what should happen. But if I plug in numbers, here's what I'm going to do. I'm going to my graphing calculator. So I'm going to do a kind of a numerical approach. Because it's kind of good for you guys to see this. Because you will encounter some functions that are not terribly obvious what happens. I mean, I showed you a pretty basic one, like, yeah, just factor, simplify, and you're good, right? So what I'm going to do is go to y equals, let's punch in the equation. If you want to follow along, that's great. If not, that's fine too. Okay. Well, I'll graph it with, just for the heck of it. Looks like a line, right? But what you could do on the home screen, if you hit alpha trace, I think I've shown this. I don't know if I've shown this to you guys. Select Y1 and treat it like function notation. It'll actually evaluate the function for you. So it's like f of x notation. If you hit alpha trace, that's where you locate it. So the first one's 0.75. So if I were to repeat that, and let's type in 1.9, I get 0.9. I think it's pretty obvious. We know what to expect, right? And the other side, just interest of time, I'll just tell you what they are. Okay.
As you get closer and closer to 2, what is y converted to? 1. And we talk about convert, and it's just different, not series, but we're still gonna use that term convergence. 1. However, if you plug 2 into this, you get 2 squared minus 3 times 2 plus 2 over 2 minus 2. What does that become? 0 over 0. What do you say when that happens? What's the mathematical amplitude, you guys know? Not undefined. It's a different term we use, but I know what you mean. It's not undefined. This is actually important that we're talking about this. Indeterminate. Okay, it's a total play on words. Let me explain why. This is actually good because some students don't know this. I do have this discussion when I teach AP Calc AV, but when they come from like pre-Calc honors or other places, they don't know, why do you call it indeterminate? Why do you call something undefined? Here's the difference. Let's do undefined first. 2 divided by 0. That's undefined. Because there's no definition for it. I have no clue. Well, not no clue. It just can't happen. It's just impossible. So undefined actually means impossible. It cannot happen. Like, for example, if I have like 10 divided by 2, of course that's 5, right? And how do we know that? Because 10 equals 2 times 5. We know that, right? 10 equals 2 times 5. However, can I multiply a number by 0 and get 2? No, there's no such number that ever exists. That's why it's undefined. There's no definition for it. It just can't happen. Now, indeterminate is a different scenario. Indeterminate, if I have 0 over 0, right? Here's the deal. If I'm, let me color code so it stands out a little better. Let me make the bottom 0 green. The bottom 0 be green. The top 0 is blue. Okay, so 0 over 0 equals a number. Here's the thing. 0 times what equals 0? Anything, exactly, anything. That's why it's indeterminate. We can't determine what it is. We don't know. So when this happens, it doesn't mean the limit doesn't exist. When this happens, the limit is usually some number. So we have to resort to graphical, algebraic, or numerical techniques to find out what it is. Numerically, you'll always be fine because just plug a number close to what x is. Graphically should be fine too. Just graph and zoom in, it's gonna happen. Algebraically, those are gonna be a little tricky. There's different techniques. One technique is factoring, which I just did and simplifying. But we're gonna think of these numerically, graphically, algebraically. We're not gonna always approach it that way, but always think of it that way and see how those are interconnected. That's when you get really good with this stuff and the math becomes more rich. You start understanding this in a more richer form. But yeah, that's usually what happens. If it's undefined, by the way, like let's say I have like 1 over x. Well, what happens at x equals 0 for this graph here? What do we call that when that happens? No, but what graphically? No, that's undefined. But what happens graphically at x equals 0 for this kind of equation? Vertical asymptote, exactly. So usually when you see this happening, I meant to put 1 over 0, not 5 over 0. My bad. When it's undefined, usually the limit as x approaches 0 won't exist, or it'll be going towards positive or negative. If you kind of look at from the left side or right side.
We'll have that discussion in part 2 later. Okay, let's go to example 2. Okay, we got a piecewise function. Now, I know that this reduces. I know it becomes this, right? So let's do, excuse me, let's do this. Graphically, it looks like this, right? 1, 2, 1, 2, 3, 4, 1, 2, 1, 2. There's a point at 2, 1. Okay. Of course, f of 2 is what? 4, right? But what is this going to be instead? Exactly. So they may not equal each other. Because we're asking about approach. That's all we care about. We don't care about what is exactly. By the way, this is not continuous.
If you were to draw this, would you have to look at your pen test off the paper off the board? Yeah, for sure. When this dot doesn't equal this limit, we lack continuity. That would also be doable with this continuity. We'll have that discussion probably on Friday or next week. I'll do that.
So 0 over 0 is independent, which means that there is such a value for a number.
For the limit, yeah.
So would there be a point there, or is it still a whole?
It depends on various situations.
There's a whole variety. We haven't broached that yet.
But like, let's take this.
Yeah, that's a whole, right?
That's a whole.
In that case, but that's not all cases.
Not all.
Yeah, we'll get there. Matthew, go ahead.
Because it's all about approach as you get closer and closer, not what's spot on. That's what the definition of limit is about approach. That's how it's defined. It's defined as approach. As you approach as you approach 2 from either side.
What it is two, but what's two, but when it approaches.
So as x approaches 2, what's y approaching? Y is approaching 1. It's all about approach. That's all it ever is.
Point doesn't matter.
No, does not matter. That's why we talk about that. Dude, go ahead.
So like, even let's say it didn't have the disassociated point or like the point, would that be continuous with the whole or that?
Still not continuous.
Yeah, that you could write it. So what happens there is that you write the piecewise function, your domain's not all real numbers. And so that's the other thing too, is that, so, I mean, I'm getting ahead of myself, but we start talking about continuity. You need to make sure if you're looking at like calling 2c. So we use the letter c a lot in this class, like when x equals c. So when x equals 2, so c is 2. First of all, it has to exist there. The limit has to exist, and the limit has to equal f of c. Of course, f of c
Doesn't equal the limit. So, but we'll have that discussion. We're getting a little bit too out of ourselves here. Okay, let's keep moving. Okay, so the implication that left and right hand limits are different. If that happens, if I call this the LHL and I call this the RHL. If those are not the same, then the limit does not exist. For short, sometimes we use the term DNE. DNE is short for does not exist.
I've never watched the movie Mean Girls, but apparently I don't ask you about this. This is 10 years ago. It's like, oh, it's really very good. I don't know what they're talking about. It's probably past your time, so don't. Oh, there's a lot. What does not exist? So, y'all done?
Yeah.
Great. And here are the notes. Here's the packet.
I use extra sheet of paper.
No problem. I'll staple it. There we go.
Thank you.
All right, let's keep moving. So the limit will not exist if the left and right hand limits are different. It doesn't matter at all what the y value is, just so you know, that doesn't matter. So for example, the limit would be that. And then what the limit equals is a number. No infinity is not a number. So like, for example, if you look at tangent x, hope you guys remember how that graph looks. Graph looks like this here. So if I'm approaching pi, so we call this a left-hand limit. That symbol right there, that's a superscript. That's just a font, right? So when you look at that, right, you look at that superscript, the minus and the little higher, that means you're approaching x on the left side. You're approaching pi over 2 from the left side. So left-hand limits, I should have wrote this down up above. Left-hand limits look like this. The limit as x approaches c with a little minus symbol. Right-hand limits look like this. The limit as x approaches c with a little plus symbol. Okay. So right-hand limits means you push from the right side, left hand push from the left side. So I should have mentioned that. So that's what this means. You're approaching pi over 2 plus. Well, what's y doing? I'm approaching pi over 2 by the way, right there. The rightmost vertical asymptote. If I'm approaching pi over 2 from the left side, what's y doing? What is that approaching, guys? Is it approaching a number? It's going up forever, right? So technically speaking, it is approaching positive infinity, but it's not a number. So typically we'll say DNE. Typically we'll say DNE because there has to be a limit, right? Limit means like a ceiling. There's no limit, right? This goes up forever. Sky's the limit. If you want to say that, we don't know. So even though you can technically say positive pi, really there's no limits. But still good to know that's going towards infinity because it might help with some other stuff we'll do later on. Okay, so this is a nice example. This is kind of your quintessential limit problem that you typically do. Like, here's a graph, got to answer questions about it. And just for my pacing purposes, we'll see how far we can get. We go to what time again? Yeah, let's see how far we get. So I want to see if we can get pretty far here. All right, so let's do this, guys. Here we go. Okay, so this is a right-hand limit. So if I'm approaching 0 from the right side, what's y getting close to, guys? 0. Now, if you don't see a superscript, yeah, you call this a two-sided limit. You call that a two-sided limit. So from both left and right sides, what is it approaching the same thing? Yep, still 0. But what's f of 0? 2. Good. Now, this is a left-hand limit. That's a right-hand limit. And that's a two-sided limit. Okay, if you're approaching 2 from the left side, what do you get? From the right side? 1. But overall, does not exist. Yes, were you looking for something, David? Oh, I don't have that on me. I'm sorry. Yeah. Okay. And lastly, what about as x approaches 3? Guys, 0 yet, right? sometimes you can just look at the y value if there's nothing weird going on. So
Yeah, there's two-sided and they're putting the same value.
sometimes that's true. Okay. Actually, I think I do have a wall chart. Hold on. Oh,
Hold on, about that. She didn't have a good spot. Oh, that's good.
here. Yeah. All right, let's keep moving, guys. Okay, one limit does not exist. Okay, so this is kind of a funny formula. Guys, quiet, please. It's actually a piecewise function, believe it or not. Hold on, let me change that. Okay. Think about outside of x.
If x is positive, then of course x leads left, right? But if x is negative, then you gotta change it to negative x, right?
Because remember, absolute value of x, in case you guys didn't realize,
Or 1.
or -1. So absolute of x could be x. Because think about graphically what happens for absolute value, right? It's y equals x if x is positive. It's y equals negative x if x is negative. Thanks, Andrew.
The formula sheet.
I got it. Good. Oh, let me hook you guys up.
No, that'll work, I guess.
And guys, I'm recording this. For those who just missed part of it, don't worry, it's being recorded. Okay, so guys, quiet please. So here's the deal. If I were to graph this, right? So really, it's getting kind of busy, so let's just focus on this then. So really, it's a piecewise function. Okay, that's really what's happening. I got myself a piecewise function. So here's the deal. What's the left-hand limit going to be? -1. What's the right-hand limit? They don't equal each other. Hence, the limit as x approaches 0 of f of x does not exist. So in this case, I did approach it graphically because I just thought for myself, yeah, I mean, look at the graph. And 0 is not part of my domain. So yeah, that's what happens. So it's a piecewise function, actually. Here's another one. A graph that looks like this, right? So the left-hand limit is pos infinity. Remember, infinity is not a number, right? So we say that doesn't exist as well. So the limit as x approaches 0 of 1 over x squared does not exist. This is also kind of a funny one. Trying to remember how this one looks. This one kind of goes haywire as you get close. Let's go to Desmos. That'll be a good idea. Yeah, it kind of goes haywire. You see how, like, as I get close, the graph does that, and that's mainly because there's a lot of yeah, because if you think about it, you're doing 1 over x, right? So what if x is super tiny? Like, what if x is 0.1, x is 0.01? There's a lot of cycles it's going through. So the graph kind of does something really funny like this. I know, it's kind of crazy, but it oscillates. I don't know. So just graph. Just graph it. So that's also considered discontinuity as well. It's called oscillating discontinuity. You rarely encounter this. We don't really broach the subject too much. But for sure, when there's vertical asymptotes, for sure, when there are holes, yeah, we do consider that. Okay, just so I feel like you guys can do some homework, let me just make sure I cover certain parts. Okay. Let me go up to finish this page and then do the example 5. We'll stop at example 5. Actually, we'll do the theorems down below as well. Yeah, I think we can knock this out in 5 minutes, guys. Let's do this. Let's go. All right. Okay. So, guys, quiet. Strategy 1, try direct substitution first. Just if you plug 4 in, you get 5. Plug 2 into x, you get 2. Plug 2 in, you get 16. So very basic, right? Always try direct substitution first. Sometimes that'll do the trick and you're done. Sometimes that's fine. There's no issues there. So conclusions, try. Yeah, sometimes f of c sometimes. Sometimes this works. The limit equals f of c. Remember, c is what we're letting x approach. Okay, questions? No? All right, limit theorems, guys, quiet. These are all intuitive, hopefully. Use intuition. So, like, this case would be f of c plus g of c. Or here, or actually, let me take it back. You told what the limit is for f of c, l plus m. The limit as x approaches c for f of x is l. The limit as x approaches c for g of x is m. So you can say l plus m or l minus m or l times m or k times l or l over m with the caveat that m does not equal 0. Or here, L raised to the R of S power. That's fine too. So you could just totally use intuition here.
As long as each individual limit exists. As long as each individual limit exists. You're adding two functions. You add two functions if you want, but they're both like really crazy, like the same f of x like x plus 5 to the third power, and leave x like log base 5 like x plus 2 cubed, whatever. You know, just do each one individually and add up the limits. Yeah.
All we're good.
You're splitting that into two limits, and then the limit of one down and one down.
Yes, exactly. 100%. Yes, correct. Correct. Right. So in this case here, I mean, if you really want to go about in a labor intensive fashion, you could do this. So in this case, you're just going to get 3 times 5. I know I went about it in a little bit more drawn out fashion, because I could just plug 5 in. But what I'm trying to show you
Is that you can decompose this expression as you know, 3 times x minus 13 raised to the third power. Great. What's limit x is x squared 5 5. 3 times 5 is 15 minus 13 raised to the third power.
So what this means is that if you have a polynomial, which I do up above, just have to see. And if you have a rational function, it's just this also. So you can just plug it in if it's all organic. It's polynomials. There's no reason for any wackiness, right?
I mean, for a rational function, of course, we won't want to be 0, but
It's all good. So I think that's perfect. That's where we'll stop for today. Okay. We'll pick this up on Friday.